I will send out a link to this video in a little while, so you guys will be able to watch it anytime you like in the next few days. Anyway, I hope that you've survived your last week of classes. We're just about done. Just have to get through next week, and summer will be here. So that's definitely good news. Let me just make a couple announcements, talk generally about a few things, and then we're going to do, of course, as I usually do, I want to give you some practice problems so you have an idea like what kind of questions to maybe expect for our test next week on Wednesday. So, but before I get to that, just a couple quick things. First of all, don't forget that I do have office hours tonight. So if anybody's still working, I noticed only 3 people have turned in the homework so far. So if you're still working on that, I will be in Zoom starting, I'm going to take about an hour break after the review session. And then around 7, I should be able to head into my Zoom office hours. So feel free to stop by if you want to hang out to ask any questions there. And then in the review packet for the final, I've already mentioned that, I have a ton of other office hours coming up. In fact, let me just pull up that review packet again. And then I'm going to share my screen real quick with you guys. So let me do that. Just want to run through this because on Wednesday, I really had to kind of go quickly because I was trying to get done with those other proofs. So this is the final exam information, just to make sure everybody's on the same page here. Don't forget, our test is on Wednesday, starting at 5 o'clock. We'll be doing this without notes or without books, but I will let you use a calculator. What kind of calculator it is, if it's a handheld calculator, that's fine. If you just want to use a calculator off of the internet, that's also fine. But just grab a calculator, make sure you know how it works, and that you can use the basic functions of it. I will let you use that. In terms of the coverage for the final, it will be comprehensive. There will be a little bit of an emphasis on what we covered in the last 2 weeks, basically after the second midterm. So what I would say is, in terms of the breakdown, let me just stop sharing my screen for a quick minute. So I would, if I were you, I would be thinking about it in these terms. The first midterm was chapters 2 through 5. The second midterm was chapters 7 through 10. And then post second midterm, we've been jumping around a little bit. So I'm just going to call this post second midterm. So, the post second midterm was really only 15% of our whole class semester time. But you might expect that could be anywhere from 20 to 25% of the final, just because we haven't had any tests on it yet. So this is a chance for me to ask some questions there. And probably from each of the first 2 midterms, you can expect a roughly, 30 to 35% breakdown. Now, I have not written the test yet, and I don't want to, sign a contract and promise exactly what it's going to end up being. But it might be something close to this, is kind of what I would be shooting for. It's also important to realize that, of course, this material is all building on itself. So the stuff in the chapters 2 through 5, basic things on congruences and the Chinese remainder theorem and Fermat's little theorem, we use that stuff throughout the semester. We've seen problems even in the recent weeks that use the material from early on. So it's not like you can sort of just draw lines through the material and break it up into well-defined groups, because you do have to know all of the topics because they might be related. You could have a question that on the surface is about one subject, but whose solution really hinges on another subject as well. So just something to keep in mind. Try not to try to put everything into a box. It doesn't necessarily fit that neatly. Now, having said that, one of the things that I think is really important is we've learned a lot of tools this semester, and knowing sort of, or having an idea of what tool to use at what moment, I think that really is how, you get a mastery of the material to the point where you're not, blindsided by any of the problems. So you see a problem, you're like, okay, I know that I need to use Fermat's little theorem to do this, or I know that I probably should find a primitive root to start solving this problem. Like, so there are certain, tools that we have, and using the right tool at the right time, or at least having an idea of a good tool to use at a particular time on a particular problem would be, something that's a good idea. By the way, this breakdown here does not include those two proofs that you're going to reproduce. Remember that those two proofs collectively, let me just write it over here maybe, the two proofs, I would suggest that that's going to be anywhere from 25 to 30% of the test. So again, I haven't exactly broken down the exam yet. I didn't really write it yet, but that's going to be a big chunk of the test, right? You want to get all of those points if you can. And so when I'm talking over here about these other chapters and so on, this is really the breakdown of the rest of the test. Okay, so this breakdown does not interfere with the two proofs. The two proofs, of course, have to do with the late material, the stuff we've done in the last 3 weeks or so. But in addition to that, of the remaining, 70, 75% of the final, this would be the breakdown. So there will be even more questions about stuff from post midterm too. In addition to the two proofs, there's going to be, of the remainder of the exam, another 20 to 25% that would be based on that stuff that we've just done recently. So you definitely want to be comfortable with things like perfect numbers, things like representations as sums of squares that we just have spent most of this past week talking about. The sigma function, the tau function, the stuff that you're doing the homework on for tonight is all related to that as well. So we're gonna do some practice problems from that section as well. But really between today's review and Sunday's review, I'm planning to sort of do examples of everything. I'm gonna try to cover all of these chapters. And the idea, again, as I always say, is you're gonna walk away from the review not necessarily ready to take the test that moment, but at least you have an idea now, okay, I need to review these certain things, and make notes to yourself about topics that come up in these next couple of hours where you're like, oh, gee, I forgot about that. Or, oh man, I don't feel like I could do this. I should probably review it a little bit more carefully. So just taking some of those notes for yourself, I think would be a great idea. And then you also can, if you're really struggling with a concept that we do during the review session, just footnote it for yourself to stop by my office hours so we can have a longer, conversation one-on-one about something. I'm always happy to do that as well. So anyway, so this is kind of an overview of what I would expect in terms of kind of the breakdown of the test. And there's a sample final for you guys to take a look at, and that'll give you something else to kind of get a handle on maybe what to expect. Here you see all these extra office hours, Sunday, Monday, Tuesday, Wednesday, pretty much every day except tomorrow. I probably won't be available, but starting on Sunday, I should be. Have another review session Sunday night. And then this is just, again, you've looked at this already, I think, just a quick list of the important terms, the theorems for the test that we've now covered all of. And then just some other theorems here that I wouldn't necessarily, some of them are in the list already, but you should just know these things: the formula for sigma, the formula for tau, the fact that they are multiplicative. We did a little group work problem where we figured out the last digits of perfect numbers, limitations on odd perfect numbers. When is a number a sum of two squares? That's an important one. And then I say here something about characterization for representing an integer as a difference of squares. Now, I actually haven't talked about that, but I'm going to use it as one of my examples in the review session. So that'll be a chance to kind of see that. And then, yeah, just basically what should you be able to do, a little bit of advice, and then a bunch of practice problems here. So I'm going to do different problems than the ones that are here because I want you to have it as much exposure and availability of topics as possible. So that way, if I don't duplicate problems, it gives you guys more stuff to look at. I think it's probably going to be overwhelming to try to do all the homework again. I would not do that. Maybe there was an assignment that you really didn't kind of do that well on, or you didn't really follow it very well. Maybe there'll be some specific little points within the homework where you're like, yeah, I probably better go back to that because I don't think I really understood it. That's fine, right? But you're not going to have time to go back and redo all the homework, right? It's just not going to happen. If you're looking for something that would be a close model of doing that, it might be to look at all the group works. The group works are, not as extensive as the homework. There's not as many problems there, but at least there you have something manageable to kind of go through, and that covers a lot of stuff from the beginning to the end of the semester. So let's see here. Just want to see if there's any. I have my chat window open, guys. So if you have any questions, you can use your microphone, obviously, but you're also welcome to use the chat feature. Somebody's asking about how to handle nerves to get. I don't want you to be stressed out. I don't want you to be all nervous and all twisted up in knots, because that doesn't help you do any better, and it just makes it a less, it's just not fun, right? The first thing is, a couple people have asked me about the fact that in my syllabus, I have this thing about how you have to pass the final in order to pass the class. And I know that makes people nervous. That's like the speed limit being 55 miles an hour, and they're not going to pull you over unless you're going 70 or something, right? See, the idea behind that is in the past, I had some students who just didn't take the final. They had such a high average that they decided, you know what, I'm just not going to take the final because I know I'm still going to pass. And I don't want that to happen. I want everybody to learn and to have a chance to sort of share what they have learned on this test. So I do want everybody to take the test. I do want everybody to take it seriously. But this thing about getting all worried that you're not going to pass the final, try not to worry about that. I said this the first day of the semester, and I'm going to say it again now, right? This is not a weed out class. Everybody who's in Math 430 is a good student. You wouldn't be here. You wouldn't make it into 400 level math if you weren't a good student. I believe every single one of you is a good student. I'm not here to sort of pick out who shouldn't be here. So what that means is I don't have to fail a bunch of people. I don't want to do that. And I doubt that I'm going to be failing hardly anybody if I can help it. I don't want to do it. It would only be, if somebody doesn't take the final, something like that, right? Then I'm well, I don't know. So try not to let that get you all worried. The second thing is I am going to give you extra time on Wednesday. So it's not going to be one of these time crunch things where, oh my goodness, I have to go fast. Because honestly, Wednesday night, I really don't have anything else I have to do. So I am more than happy to let you, take your time, really mull things over and do the best you can. So that's something to keep in mind. I will let you know, if it's been going on long enough, at some point I might say, hey guys, we're probably going to wrap this up, but I'll give you plenty of advance notice about that. So try to just take your time, and skip over something if you don't get it immediately. Please know that I don't expect perfection. I'm not, and you don't have to be perfect on the test. You have to know what a perfect number is, but you don't have to be perfect. in the sense that, if you draw a blank on something, right, don't let it stress you out and that's all you can think about in your mind during the exam. Just let it go and try to work on the rest of the exam with a clear mind. Now, if you have time, right, which as I said, I'm going to try to give you plenty of time, sure, come back and think about it some more a little bit later, but I would not, or maybe write down what you do know. Maybe you don't really see how to do the problem, but you have a feeling, oh yeah, I think I probably need to use, the Chinese remainder theorem for this. I just don't see how. You can make some notes to that effect because I can give you partial credit for everything that you know. So often students will ask me, oh, can I have a cheat sheet? Can I write up a note card or something? The thing about doing that is then I don't feel like I can give you credit for all of your knowledge. Then everything comes down to, did you solve the problem or not? Right? But if you don't have that note card and then I ask you to solve a problem and maybe you don't know how to fully solve the problem, but you can write down certain steps or, what theory is related to that problem based on your knowledge, not just based on reading a note card, then I can give you credit for that. So this happens in all of my classes. People want to have a note card and I'm like, why? If you can just learn the formulas and learn the theorems, then when you write them down, I can give you points for them rather than saying, well, this was already on the cheat sheet, so why would that be worth anything, right? So that's really my reason for not letting people use notes and books on exams, because I want to give you credit for knowing those things. Let's see, there's a couple of things coming into the chat I want to try to address. Ben is asking, should we expect a take-home part like we did on the midterms? That is a possibility. The only problem with it is that you guys have other finals, and I do want to be a little bit conscientious that you do have other studying to do. You don't want to have to do a lot of other outside stuff. I might be willing to let you take a part or maybe 1 or 2 parts home, but it's not going to be a lot. Okay, so it would be just a small little thing. Did you guys like having that choice with the midterms? Was that kind of a good thing? I see a lot of people nodding yes and saying yes. Well, maybe I will do that then. Yeah, and I'll probably that way you have, again, something to relieve a little stress maybe, that you can choose something to take home and have a couple of days to kind of take your time on that. That's totally okay with me. Okay, so I'll probably do that again. I'll give you that choice. Tuan is asking, we don't need the list of, I am going to give you the same exact, the same table that you had on the second midterm, which has all of the primes and their smallest primitive roots up through 1,000. So you'll have all of those numbers again. And then what's considered a passing score on the final? Oh, so, again, Brandon, don't take that syllabus comment too seriously. But you know what my scale is. So whatever's passing on that scale, I think it's 65% to get a C would be passing. But again, if somebody takes this test and gets like a 50% or something, which technically is not passing, but then if I average out their grade and they come out, well above a C range, no problem. I'm not going to fail anybody in that situation. I just want people to show up, take the exam and take it seriously. And, I just don't want people saying, well, I have a 99% right now, so I'm just not even going to deal with this class anymore. And believe it or not, I have had people who have done that in the past. That's what motivated me to then put this into the syllabus. But again, try not to let it distract. As long as you show up on Wednesday and give it a good effort for 2 hours, I don't see that syllabus comment coming into play at all. Okay. Anyway, I think I've gone through the review sheet for the final. I would recommend you try the sample final. Don't try it until you've actually studied a little bit though first. If you try to do it like now and you haven't really studied, you probably will only make yourself nervous because you're gonna be like, oh, gee, I don't remember this stuff. And then maybe the sample final is kind of stressful. I would wait until, at least Monday, if not Tuesday, early next week, so you can do a little studying over the weekend first, and then maybe try the sample final. You should leave yourself enough time to sort of do a review of that sample final. So don't take it like right before the actual final. I would take it maybe 24 to 48 hours before the actual final. This is just my advice on that. Okay. Does anybody else have any questions logistically or just about the philosophy of the exam, kind of what to expect in terms of the, the timeline and the breakdown that I've got here? Is this all giving you at least some idea? You've already taken a couple of midterms with me. And so you kind of know my style of my questions. My exams don't tend to be too short. I'm going to try my best to, maybe I need to take like a sedative before I write my exam or something. I get really excited. It's not that I'm trying to be too crazy with it. It's just, I love the questions. Like, oh my gosh, this is a good problem. But the problem is that then I come up with too many of those. So I'll try my best to kind of keep my blood pressure under control and just stay calm and write my questions and be done with it. But again, if I screw up and it's a little bit too much, I am going to give you extra time as well. So that I hope will be a little bit of a help. Okay, so well, if there are not any other immediate questions about the test itself, I think what I want to do for the rest of our time here today is start working on some practice examples. These are problems that are not in the sample final, they're not in the review packet, right? Some different examples so that we can just practice a little bit. Okay, so let me come up to my board and I'm going to jump around. I want to do a variety of topics, but I'm definitely going to try to hit some of this post-second midterm stuff, because some of that stuff, we haven't had any homework on it and it's just been kind of in the background. So let me grab this problem that I want to do. Okay, so let's get started with some actual review problems. So let me start down here. I'll write down number 1. What I want to do is decide which numbers below are representable as a sum of 2 squares. Okay, so we could try this. And let me get some numbers up here. I'll write all of them down so we can start working on these. Oh, and guys, if you have a calculator right now, it might not be a bad time to have a calculator handy even for the review, because you might see some things that you'd like to do some calculations with. Oh, I did want to say, guys, I do reserve the right on the final to say, don't use a calculator on this problem. Like there may be a problem where I say, I don't want you to actually, just brute force an answer with a calculator. So I will make that clear if that's my intention. But for something like this, I'm perfectly willing to let you use a calculator. Okay, so why don't you think about that while I erase my board a little bit here. So these are some reasonable sized numbers. They're not too small, but they are, relatively small enough that maybe with a calculator you could make some progress. Can somebody tell me what's the first step to solving this kind of question? What would you be trying to do first?
We would want to turn this number into the form n squared times m, where m is square free.
Okay, exactly. So in other words, coming up with a prime factorization, right? So exactly, because we have a theorem. I'll write the theorem on the board while you guys continue to work on this. It's theorem 13.3. Get my notation for this. Just to recall this. 13.3, we're going to write n as capital N squared times m, where m is square free. Okay, and then the answer is yes, if and only if m has no prime factors of the form 4k plus 3, right? So, oh, and then for those that are representable as a sum of two squares, let's see if we can actually write down the representation. So I'll just add that here. Write the representation. And I'll just say if possible, if it's possible to do so. Okay. Has anybody gotten anywhere on the first one by chance? Just curious what you think about 5625.
I think it's 5 to the 8th times 2 cubed.
5 to the, no, there shouldn't be any factors of 2 in it. It's an odd number. Does somebody else have the factorization yet? I can see, oh, in the chat, here we go. 5 to the 4th or 5 to the 5th, Brianna? I'm not getting a consistent answer here, so why don't we try it again? You can use a calculator, divide as many factors of 5 out of this thing as you possibly can. 4th. Okay, so that's okay. So at least 3 people in the chat have the same answer, so I'm pretty sure it's probably true. So for part A, 5625 is equal to 5 to the 4th times 3 squared. Okay. So can somebody tell me what is the capital N and what is the little m in my expression for theorem 13.3? Yeah, you see, this integer has no square free part at all because every prime factor occurs an even number of times. So in fact, we can think of this as, 5 squared times 3 squared and then times 1. In other words, capital N is just 5 squared times 3, which is 75. So clearly m, which is 1, right? This is m right here. And this part right here is n. Clearly m does not have any prime factors of any form. Right? So the answer is yes. This one is representable as a sum of two squares. And how can we do it? How do we write 5625 as a sum of two squares?
1 squared plus 0 squared.
No, it's not quite that simple. Let's think about it a little bit more here. The point here, guys, actually, this is a little bit of a trick question. Because the m is 1, your number is already a perfect square. Namely, it is already, what, 75 squared. It's already 75 squared. So I actually gave you a number that was a perfect square to begin with. And so how do you write it as a sum of two squares? Well, you simply add 0 squared to it. Right? So this is it. This would be the easiest way to do it. It's just the whole number 75 squared plus nothing else. So anytime you have a number that's already a perfect square, it is sort of trivially representable as a sum of squares. It's just itself plus 0. And that's a sum of 2 squares. Does this one make sense, guys? 5625, it's a perfect square. It's just a big enough number that you can't just kind of do it in 2 seconds. You actually have to factor the number out first and recognize that there is no square-free part there. Okay? By the way, when you're working on factoring a number, remember that you can just calculate possible prime factors that go up to what? The square root of the number. So like if I was looking for prime factors of 1, 1, 1, 1, those prime factors, if there's going to be any factorization, the prime factors would have to be, there'd have to be at least one of the prime factors would be less than the square root of 1, 1, 1, 1, which is somewhere in the 30s. It's not that big of a number. So there's only a handful of primes that you would need to test this number with. And again, a calculator would be a really good tool here. So let's look at part B, if everybody's okay with part A. I do have my chat window open, guys. If there's questions, I'm in no rush. So, don't feel bad to ask a question. We're all friends here. We're all trying to learn it and do well together. So it's okay to slow me down and pick on any points that maybe you're not 100% solid on. Back over here. So for part B, we have 1, 1, 1, 1. Has anybody figured out how to factor that yet? It looks pretty tempting that 11 is a divisor, doesn't it? And it is, right? So Tuan actually put it in the chat for us. This is just 11 times 101. So this time we have just 11 times 101. Based on that factorization, right? Can you tell me what is capital N and what is the little m in my theorem this time? Let's see. Yeah, in this example, guys, there is no square at all. This is like almost the opposite of part A, right? So the capital N this time is 1. The square free part is this entire little m here. So we can look at these factors of little m and we can ask ourselves, are any of them of the form 4k plus 3? And what you can see is that 11 has the form 4k plus 3, right? It's congruent to 3 mod 4. So I'm just going to say since 11 has the 4k plus 3 form, then the answer this time is no, right? According to our theorem, if there are any factors at all of the form 4k plus 3, then the answer is for sure no. So this number is not expressible as a sum of 2 squares. Does that make sense? It all comes down to the prime factorizations of these numbers. That's really the key. Okay, let's go ahead and move on. Is everybody okay with part B? We just factor our number, use a calculator to help you if you need to. Once you've factored it, you have to identify what little m is, and then ask yourself about the prime factors of little m. And in this case, we do have one of our prime factors has the form 4k plus 3. All it takes is one prime factor of that form to mess the whole thing up, right? So this is why we have a no right here. Okay, so let's go back. I'm gonna put the third one here as well. Let's look at part C. 2818. 2,818. First thing we need is the prime factorization. Try to figure out the prime factorization of that.
2 times 1409.
Okay, so obviously there's a factor of 2, Brandon, very good, and then that's multiplied by 1409. And again, 1409 is, you know, just big enough to be annoying, but you can run through the possible prime divisors that are, you know, less than the square root of this. The square root of 1409 is about 38 or something, I think. You can check it with a calculator. So there aren't very many primes that could possibly divide into 1409, and you can just check that none of them do go in there. So that means that 1409 is actually a prime. So again, this is a number that is completely square free. The capital N is just 1 again, and my little m is 2 times 1409. And you can just check. Well, you can see that in mod, well, first of all, obviously 2 is not of the form 4k plus 3. 1409, remember that if you're interested in what a number is congruent to mod 4, you just have to look at the last 2 digits. So in this case, we just look at the 09 and we ask ourselves, is that congruent to 1 or to 3 in mod 4? And the answer is it's congruent to 1. So this whole number, 1409, is congruent to 1 in mod 4. You with me on that? So the point being, see, if you take any number, just as a quick little side comment, you remember if you take a number and you write out its decimal digits, right? So if you write out a factorization, now this isn't really a factorization, but if you write out a base 10 decimal representation of n, and then you reduce it in mod 4, right? Since 100 is a multiple of 4, right? Then basically all of the terms 100 or 1,000 or 10,000, those are all congruent to 0 in mod 4. So all that you're left with, this is in mod 4, all that you're left with when you're looking at your number in mod 4, you just have to look at the rightmost 2 digits and just make a number out of those. So in this case, we would be looking at 09. Those rightmost 2 digits in mod 4, and that does come out to 1. This makes sense? So in mod 4, 1409 is congruent to 1. So m has no factors of the form 4k plus 3. And so this implies that we have a yes here. This one is yes. Now this question is asking us to also write out the expression as a sum of squares. So I'd like to try that with you guys. So we want to figure out how to write 2818 as a sum of 2 squares. The trick to doing this is to remember the lemma. To remember the lemma that says that if I can just simply figure out, so I write out my factorization here. If I can just figure out how to write each factor separately as a sum of two squares, right? So if I can figure out how to write 2 as a sum of two squares, and then 1409 as a sum of two squares, then I can use this expression to write out the whole number 2818 as a sum of two squares. I'll remind you what that formula is in just a minute. But the first thing I want to do is figure out for these numbers, what are the A, the B, the C, and the D? Anybody want to tell me what should A and B be equal to? They're both equal to 1, right? Exactly. So we're just going to write this as 1 squared plus 1 squared. Okay. And now we have this number 1409 that we're trying to write as a sum of squares again. Now again, one of those two, these numbers cannot both be very big. Because as we said a minute ago, what, 38 squared approximately? Approximately 38 squared is already 1409. So you're not going to have C or D being bigger than, say, 38. They can't be. Neither one of these numbers is going to be bigger than 38. So I should have taken my own advice and brought myself a calculator. Let me just this is a good one to use a calculator to help us with. I'm just going to pull up my own little calculator here. So if I calculate 38 squared, I actually get 1444, which is already bigger than 1409. So whatever these numbers C and D are, they have to be less than that. So does anybody have a suggestion how we're going to figure out C and D for a number like 1409? I only have one idea. Brandon?
I just ran a bunch of numbers through my calculator and got 28 and 25.
There you go. That's it. It's really just trial and error. What you can do is you can just say, well, let's just square a number and subtract it from 1409 and see if you're left with another perfect square. So it turns out that if you just try 28 squared, you get 784. And if you then subtract that off of 1409, you actually get 625. And it just miraculously happens to be the case that that's a perfect square as well. So I'm just going to say here, essentially by trial and error, this is where, having a calculator and, some time to work it out, I bet everybody in here could come up with this answer. It might not happen in the first 10 seconds, but I also don't think it's going to take you 15 minutes. It should take you maybe a couple minutes at the most, right? To just do a little trial and error and come up with that. Okay, so once we have done that, now we can go back and remember our lemma from this past week, which tells us how to take the A, the B, the C, and the D and get a perfect square out of it. Namely, do you guys remember this? This is the formula. This is worth knowing. AC plus BD squared plus AD minus BC squared. Yeah? And at this point, we have all of these values. A is 1, B is 1, C is 28, and D is 25. So if I just, A times C plus B times D, that looks like 53. So we have 53 squared plus, and then we have to do AD minus BC, which is actually -3. But we don't need the negative. We can just write it as 3 squared. So we should be able to check. Of course, with a calculator, you can also check if this is correct. Take 53 squared, take 3 squared, add them up. You should have 2818 on your result. That make sense, guys? Okay, so are there any questions about using this theorem? Are you guys, we didn't have any homework on this. We did a couple examples during the lecture this past week, and then we've done a few right now. Does everybody feel like they understand how to kind of do this sort of a problem if I were to ask another one? The beautiful thing about number theory is it's so easy for me to write questions because there's so many numbers out there. I just have to pick a new number and I've got a new problem. so you should be ready for that. I might do something like that next week. Okay, I'll go ahead then, and I'm going to assume that you guys are pretty happy with that, and we're going to go on to something else. It's a little chilly out here because I opened my garage door, so that's why it's not erasing as nicely as I would like. I probably should have turned on my heater, but oh well. Maybe I'll do that here while we look at another problem. Okay, so let's try another problem. I'll call this number 2. Okay, if everybody's ready. So let's do this. Let's prove the following. Do a little proof here. That n, which is a positive integer, is representable as a difference. So this is related to the topic we were just talking about. A difference of 2 squares if and only if n is not congruent to 2 in mod 4. Okay, so I'm going to let you guys think about that for just a moment. I am actually going to turn on my heater again. And it's going to take me a minute to get this set up. It's just amazing. The temperature is so critical to how well this board will erase for me out here in my garage. So let me get a little heat on my board so that this doesn't become a bigger problem as the night goes on here. Okay, I'll let you guys think about that for just a moment. How we could prove that. Try to focus on the forward direction. That's what you want to focus on first, I think. I'm going to suggest that we approach this forward direction by way of contradiction. So, in other words, what we're going to do for the forward direction is I'm going to assume that n is congruent to 2 in mod 4, and I'm going to also assume that n is a difference of 2 squares. I'll just say a squared minus b squared for some integers a and b. Let's start off with that as a good starting point. Great. So we have a number that is congruent to 2 in mod 4, but it's a difference of 2 perfect squares. Does anybody have any thoughts? Maybe you don't have the whole solution yet, but do you have an idea what we might want to think about here? It's actually related to part of what we had to do in one of our theorems, one of our big theorems that's in your list that we proved this past week. You might remember that we were trying to show that a number of the form, a prime of the form 4k plus 3 is not representable as a sum of two squares. You remember that? We had, I think it was theorem 13.2, which says that a prime, an odd prime, is expressible as a sum of two squares if and only if it is congruent to 1 in mod 4, right? So forget about this problem for a minute. Let's go back to theorem 13.2. An odd prime is a sum of two squares if and only if it is congruent to 1 in mod 4. The way we prove that is we said, look, if we square a number in mod 4, the only possible choices are, do you remember? If we square a number in mod 4, what could it be congruent to? Yeah, almost, Ben, not quite the whole list. Oh, yeah. I'm sorry. You're right. 0 or 1, right? If we square a number, so let's just recall that. So note that a squared is congruent to 0 or 1 in mod 4. If you square any number in mod 4, it's either congruent to 0 or 1, depending on whether you're squaring an even number. If you square an even number, you're going to get 0 in mod 4. If you square an odd number, you're going to get 1 in mod 4. B squared is congruent to 0 or 1 in mod 4. So both A and B are congruent to 0 or 1 in mod 4. Does that help you to see why A squared minus B squared being equal to N is not going to work? This is not going to work, right? Because you're taking either a 0 or a 1 and subtracting either a 0 or a 1 from it. You're not going to get 2 out of that in mod 4, right? So we could actually, a nice way to do this would maybe be with a table. And what we could do is make a little table here with all of the possible congruence values of A and B. So this would just be a one way to prove this. 0, 0, 1, 0, 0, 1, and 1, 1. I'm sorry, this is A squared and B squared. Sorry, in my table, I'm writing A squared and B squared. These are the only combinations. And so if you subtract, right, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is 3, and 1 minus 1 is 0. This is in mod 4. So in no case is it possible for N, which is equal to A squared minus B squared. This is N actually right here. We can just put that down in the table. So N is either congruent to 1, 0, or 3 in mod 4. So this proves from the table that N is not congruent to 2 in mod 4. And that's your contradiction. Right, so we're looking here for a contradiction. So we get a bit of a contradiction out of that. Does that much make sense?
Dr. Annan, do we have to assume the contradiction? I mean, do we have to assume to show the contradiction, or can we just put the table and say, hey, this is not like equal to 2?
Yeah, you can do it basically by contrapositive, which is equivalent to contradiction. So if you didn't make this assumption in the first place, right, you could have just, started off saying, assume N is representable as a difference of two squares, and therefore by this table, it's congruent to either 0, 1, or 3 in mod 4, and therefore not 2. You don't really have to do the contradiction. Is that your question?
Yes, thank you.
Yeah, absolutely okay to do that. Okay, great. So now the backwards direction, by the way, the backwards direction is not as, like, this is the part that I really wanted to make sure we practiced, because this is related to something that was done this past week in one of our big theorems. So I wanted you to kind of see this again. In fact, on Sunday night, I'm going to do another example where we do something similar again. But right now, I am going to go ahead and prove the backward direction. This is a little more pulling something out of the sky that you're probably going to say, gee, I'm not sure I would have come up with that. And that's okay. So don't get too stressed out about the backwards part. I just wanted to make sure the forwards part was good. For the backwards part, of course, we're going to assume that n is not congruent to 2 in mod 4. And so that leaves 3 possibilities, right? So, we can go through the 3 possibilities. So case 1, we could assume that n is congruent to 0 in mod 4. That's one possibility, right? And what I'm hoping to do is represent n as a difference of 2 squares in this case. I'm proving from right to left. So I now have to show that n is a difference of 2 squares. And this is what I meant by saying this is a little bit of a trick out of the sky. You may look at this and say, oh my goodness, how did he come up with that? Don't worry about that. Just make sure that you understand, once I write it down, that it works. Okay, so here's the idea, is I can actually write n in the following manner. N over 4 plus 1 squared minus n over 4 minus 1 squared. Okay. First thing I want you to notice is that because n is congruent to 0 in mod 4, n divided by 4 really is an integer. So you're not really creating any fractions here. This is an integer squared minus an integer squared. The other thing is that when you actually multiply this out, almost everything cancels out. The n over 4 squared cancels out with the n over 4 squared. The 1 squared cancels with the negative 1 squared. The only thing that doesn't cancel is the cross term. And the cross term here, the cross term of the first part is n over 2, right? And the cross term of the second part is actually negative n over 2. So that's why it's equal to n. And you can see that is what it's going to come out to be when you get done with that. Okay. So that's one case. Another case, well, it actually turns out that I'll just do case 2. Let's just assume that n is congruent to 1 mod 4. Okay. Again, we have to do basically a similar trick. And the trick is the following. This time we need a slightly different trick. But what we're going to do is we're going to write n as n plus 1 all over 2 squared minus the quantity n minus 1 over 2, n minus 1 over 2 quantity squared. So again, it's kind of just a trick that you don't need to worry about. I would not ask a test question where you have to somehow think of this in the stress of the exam. But again, the idea is that now n is odd. So if you add 1 or subtract 1 from n, you get an even number. So it's legitimate to divide by 2. You still have an integer there. And once again, if you were to expand all of this out, you quickly realize that, well, most of it cancels. The only thing that doesn't cancel is the cross term here and then the cross term here. The cross term here is, again, well, it's actually 2n over 4 and then minus negative 2n over 4. So this all just cancels out again and leaves you simply with n. Most of it cancels out. You're just left with this cross term. And I'm just going to say that that's actually exactly the same as case 3. I won't spend any more time. Case 3 would be n is congruent to 3 mod 4. And in this case, I'm just going to see case 2. We just go back to the previous case and it works out just great. So we can go ahead and get away with that. All right, so the backwards direction, you know, is a little bit hocus pocus, so grab something out of the sky that works. Not really so beneficial, but I do like the forward direction. I think that idea of looking at perfect squares in mod 4 and realizing you can only get 0 or 1 is kind of a neat idea. So I wanted to show that to you. Okay, great. Everybody all right so far? Let's combine this topic with the previous week's topic about perfect numbers. Okay, I'm going to try to do a proof. I really would like to save this one for the final, but it's too good. I can't save it. I have to show it to you. Okay, so let me erase this and give myself a spot to write another problem down, which is the following. Number 3, prove. I'm going to prove the following, guys, that every odd perfect number is the sum of 2 squares, or can be represented, can be represented as a sum of 2 squares. I love it. You see what's so ironic about this statement? We have yet to even give one example of an odd perfect number, and in fact, we don't even know if there are any. It's that philosophy that we used in chapter 11. How are you going to prove that there are no odd perfect numbers? Well, what you're going to do if you're interested in this kind of research is you're going to suppose you have an odd perfect number, and you're going to try to say as many things about it as you can, hopefully enough things to eventually have a contradiction. So this is yet another thing we can say about these mysterious odd perfect numbers, if they even exist, is that they can be represented as a sum of 2 squares. Anybody want to throw out a possible starting point here? All right, let n be an odd perfect number. Ben, I think that's as good a place as any. Let's do that. So solution, let n be an odd perfect number. I was talking earlier, guys, about making sure for the exam, you know, we have all these tools. You have to know like which tool to use at which moment. Well, the thing is, with perfect numbers, with odd perfect numbers, we really only said one thing about them. And so that must be the tool that we're going to use, right? What's the tool that we're going to use? The one thing that we said about odd perfect numbers. There's a lot of Euler's theorems, Tuan. Let's get more specific. I think you're thinking of the right thing. Yeah, theorem 11.7. Now remember, guys, I'm not going to ask you on the final for theorem numbers or corollary numbers, but for right now, while we're all referencing things and trying to kind of keep straight where everything fits, it makes sense to do that. So what this theorem says, this is one of the theorems that's in your list, right, of theorems that you could choose to learn, is that then we can write n as P1 to the K1, P2 to the K2, sorry, P2 to the 2J2, P3 to the 2J3, and so on, up to PR to the 2JR. This is the prime factorization of n. These are distinct primes. So these p sub i's are distinct primes, just to be clear about that. And the condition was that P1 is congruent to K1 is congruent to 1 in mod 4. Okay. So that is a good starting point. And we would like to prove that this number is representable as a sum of two squares. So we have our theorem for that, don't we? The one that we practiced already today. What are we supposed to do again? We're supposed to write this number as like a capital N squared times some square-free number, little m. Well, I can already tell. Look at the primes starting with P2, P3, and so on. You see they all have even exponents here, right? And the first exponent is actually odd because we have this condition here about K1 being congruent to 1 in mod 4. I'm actually going to suggest that it would be useful for us to write this K1 as, 4 times something. Let's say 4J1 plus 1, right? So this would be for some integer J1. So we could actually express K1 in that manner. And so then if we look at what we have, what we've actually got now is P1 to the 4J1 plus 1 times P2 to the 2J2, and so on up to PR to the 2JR. And what we want to do, guys, is try to use that theorem 13.3. This problem is using 2 of the 5 big theorems on your list in this pretty short solution, actually. What I'm going to try to do is write this as something squared times my little m over here, right? So what's going to go right here is going to be what I call capital N. And then what I'm going to write over here in a minute is what we always call the little m. Just want to get it into the form that I can use my other theorem, 13.3. So why don't you guys take a minute, see if you can write it down. See if you can fill in what goes here and what goes here. I'm going to give you guys a minute to do that. And then take a look at the theorem and see if you're getting what you want from the theorem. So when you pull out the squared here, it's sort of like you're, factoring this exponent, these 2's outside. So for example, just to kind of start filling it in, right? You would see that, for example, the PR would now be raised to the JR power, because when you square that, you'll get the 2JR power, right? And I can just work my way backwards and figure out what all these other terms are going to be. You're going to have P2 to the J2 power. And what is going to be the power on the P1? What power should the P1 have right now, do you think? This one's a little tricky because this is an odd number. So I can't, somehow pull a 2 out of it. But what I can do is I can kind of just forget about the +1 for a moment, which is what Tuan is suggesting in the chat. If I just forget about the +1, my exponent would have been 4j1, and that I can pull a 2 out of. So this would be 2j1, right? And then that leaves me over here with one more factor of P1, which is actually what M is. You guys kind of following me on this? So you have to know the theorem 11.7. We write down our factorization of n. We look at our exponents. Most of them are even. Any even exponents can be sort of, you can suck a 2 out of it and write it as a perfect square of the whole expression. There's just one leftover copy of the very first prime right here. And now that we have it in the form of capital N squared times M, then we're just going to simply note that since M is just a single prime, right? It's just literally, it's just P1. And this one has the form for, I'm going to call it 4L. I just want to use a different letter. I don't want to use the K or the J again. But you see that this first prime, see, take a look right here what the theorem 11.7 told us. P1 also has the form of 4L plus 1, right? Because it's congruent to 1 in mod 4, right? So thus, by theorem 13.3, right, little n is representable as a sum of squares. Right. So we can represent that one as a sum. I really like that problem because it's not that long, but it uses two of the big results that we just did in the last couple of weeks. This would be a perfect test question, except that I just used it in the review. Although it's so good that who knows, maybe I would just decide to ask it again. I don't think anybody would object to that, right? It's just one of my favorite problems. Okay, I will take that into serious consideration. Seriously though, are there any questions about this proof? Okay, great. Yeah, we've never seen this problem before. Be a perfect test question. Okay, let me go ahead. I'm gonna start over at the top again. I'm gonna do one more problem that's about this recent material, and then I know some of you want me to show some earlier stuff, so I will get back to that too, but I wanna do one more. I'll call this number 4. And this one says, prove that a number of the form 3 to the I times 5 to the j. So a power of 3 times a power of I. This is simply where I and j are greater than or equal to 0. I and j are greater than or equal to 0. That this number can never be perfect. Can never be perfect. So here's a whole nother collection of odd numbers that are definitely not perfect, right? So we're chipping away at that conjecture that there are no odd perfect numbers. We're taking a whole bunch of odd things and proving that they're not perfect. It's kind of the idea here. So no number of this form, no number that is just simply a power of 3 times a power of 5 could ever be perfect. Any suggestions how to, this one we're not going to find a big theorem to just, bulldoze this proof out, right? We're going to actually have to kind of work on this one a little bit. Any thoughts on a sort of a approach here? I don't need the whole solution yet. I'm just wondering if anybody has any ideas sort of how to frame this for ourselves. Tuan, you have a suggestion in the chat by cases. I'm wondering what your cases, if you have an idea, if you could be more specific, like what kind of cases are you thinking of?
I guess we can start with I and J both being equal to 0, and then have one of them be equal to 0 and the other one not, and then finally have both of them not be equal to 0.
We certainly could do that. We could consider, you know, one of I or J being 0. So that would be just powers of 3 and then powers of 5. But then ultimately, we're going to have to look at the hardest case, which is the one where I and J are both not 0. And I will save you the headache of writing out the first two cases by basically telling you that it's all in the last case. In other words, if you just do the last case, it'll do the whole proof. So yeah, let's just prove that we don't really, it's not a bad suggestion. It's just that those easier cases where I is 0 or J is 0 is not going to help give us any insight, I don't think. At least I didn't get any insight into how you're going to generally do the proof here. Brandon, I like your idea of doing it by way of contradiction. Yeah, let's suppose that this number is perfect, right? Suppose that 3 to the I times 5 to the J is perfect. So in other words, this is a by way of contradiction here. We're kind of going to do this by way of contradiction. Okay. So what can we do with that? What's the definition of a perfect number again? Yeah, the definition is that sigma of n is equal to 2n, right? So in other words, we're saying here that sigma of 3 to the I, 5 to the j is equal to 2 times 3 to the I times 5 to the j, right? So sigma of n is equal to 2n. And we have this multiplicative property of sigma, don't forget, from chapter 6, right? Remember, this is actually, let me work to the left here for a minute. This is sigma of 3 to the I times sigma of 5 to the j, right? So it's multiplicative. If 3 and 5 are relatively prime, then we can split the sigma into two parts, sigma of 3 to the I and sigma of 5 to the j. And Ben has another thought in the chat, which is really good, which is we have a nice formula for sigma of a prime power. Remember, what is sigma again? Sigma is the sum of all of the divisors of a number. So what we have here on the left is actually 1 plus 3 squared plus dot, dot, dot plus 3 to the j, 3 to the I. And we're multiplying that by 1 plus 5 squared plus dot, dot, dot plus 5 to the j. And we're saying, okay, that's equal to 2 times 3 to the I times 5 to the j. Right, so we're adding up all of the divisors of 3 to the I right here, and all of the divisors of 5 to the j are just right here. And there is a nice formula for this, for these geometric series. And when we were talking about sigma and looking for formulas for it, we actually wrote down these formulas. So on the left side, this expression, this summation on the left side, I'll just remind you, this is worth knowing, guys. You should know this even beyond Math 430, right? You know, a lot of you, if you're going to teach high school, you might be wondering, well, why do I need to know a lot of this number theory? Well, this is certainly something that I think any math teacher kind of at any level would be benefiting from knowing. If I want to add up powers of a number, there's a nice expression for it. Same thing with the second one. This one is going to be 5 to the j plus 1 all minus 1 over 5 minus 1. Okay, and that's equal to 2 times 3 to the I times 5 to the j. Okay, we just use the formula for the sum of a finite geometric series here. This is the idea. Does anybody have a suggestion what maybe we would do with this equation? We're looking for a contradiction ultimately. Is there a suggestion just for a next step? I'm not really ready to see the contradiction yet, but I'm wondering if anybody wants to propose either with a microphone or with the chat, what might be a good thing to do here. You know, it's very hard for us to get contradictions when we've got fractions everywhere. So it's a really good idea, Ben has it in the chat, to take the denominators and move them to the other side. This is a denominator of 2, and this is a denominator of 4. So if I actually take the 2 and the 4 and I move them to the other side, it would be a factor of 8 on the other side. Let me just leave the numerators over here. So I'm just going to get rid of the fractions, in other words. I'm just going to get rid of the fractions. So we're going to get 16, 3 to the I, and then 5 to the j. So I just move the denominators over to the right side, and now instead of a 2, I have a 16 over there. Okay. And my suggestion now is going to be to just FOIL out the left side. So if I'm just going to do a little algebra here, if I just multiply this out, 3 to the I plus 1, 5 to the j plus 1, and minus 3 to the I plus 1, minus 5 to the j plus 1, and then plus 1 equals 16 times 3 to the I times 5 to the j. Okay. Now it kind of looks like we have a mishmash of non-comparable terms, which is like the worst thing in the world when you're trying to get a contradiction here. Right? We've got a term that has powers of I and powers of j together. We've got a constant number. We've got just some powers of j and just some powers with I. And then here we have a combo again. It's like, is there any way to like combine anything here? Or are we kind of just stuck looking at apples, oranges, pears, strawberries, and peaches as 5 separate things that can't be combined? Out of these 5 terms, notice there's 4 of them on the left side and 1 on the right side. Out of those 5 terms, there are 2 of them that are similar to each other. That, in other words, that involve the same kind of expression. You see, the very first term here on the left has powers of 3 and powers of 5. The only term on the right has powers of 3 and powers of 5. These 2 terms, actually, I claim they are more alike to each other than you may realize. Take a look right here, guys. 3 to the I plus 1, 5 to the j plus 1. If I pull one of the 3's and one of the 5's out, what will I actually have? I'm going to pull one of the 3's and one of the 5's out. That's 15, right? And then that leaves me with still I factors of 3 and j factors of 5, right? So we end up with this. This is kind of the tricky step. This is the step where you have to make that sort of trick in your mind to see how to break this down. I want to make the first term on the left look like the term that's on the right. And by pulling a 3 and a 5 out of the first term on the left, I can do that. Because I want to compare them. I want to like simplify this thing. So I've got 15 apples on the left side, and I have 16 apples on the right side. So guess what I'm going to do? I'm just going to cancel things over, and I'm going to be left with negative 3 to the I plus j minus 5 to the, sorry, I plus 1 minus 5 to the j plus 1 is equal to 3 to the I times 5 to the j. Anybody see anything wrong with that? I'm looking for something glaringly staring at you. The left side of the equation and the right side of the equation, I claim there's no way they could be the same.
The left is negative and the right's positive.
Exactly, Brandon, exactly. Look at all these negative signs on the left side, right? You have at least 2 negatives here. And so you're subtracting, at a minimum, you're going to be subtracting what, minus 3, minus 5, and then adding 1 to it. This is negative. This left side here is negative. But obviously, the right side, which is just powers of 3 and 5, is positive. So this equality is actually a contradiction now, right? It has to be totally a contradiction. So this is now our contradiction. That is a contradiction. Does that make sense, everyone? This problem, you don't see the answer in 10 seconds, right? There's several steps that you go through, but I would argue that most of these steps are kind of, you know, what you would think you would be doing, right? You write out sigma of everything, simplify it, and work with the equation until you see a contradiction with it. This is really the whole approach to this thing. So I hope that that is a reasonable a reasonable solution. Any questions on that one? Okay, if not, let's do another problem. Let's do some, I've done quite a bit on perfect numbers. I've done quite a bit. I haven't done everything on perfect numbers, of course. You know, we haven't talked much about even perfect numbers. We do have a theorem for that, but I'm going to save, maybe I'll talk about even perfect numbers on Sunday night. And then we've talked a lot about representing a number as a sum of squares, sum of 2 squares. So let's go back and review some of the older material just to kind of get it back into our mind again. And then, you know, I think this is, at least we've gotten a good start on some topics from these last 2 or 3 weeks. But let's go back into some older material. Okay, so I'm going to call this number 5. Find all solutions. Find all solutions, and then I'm going to say here, if any. So a lot of times in number theory, the question is there any solution at all? Okay, so we're going to do a few of these. So I'm just going to start off here with part A. And part A is going to be x congruent to 5 mod 8. And then secondly, x congruent to 11 mod 18. Before we start solving this problem, I want to talk a little bit about, again, kind of the exam itself. Because you have a calculator, you probably could get the answer with a calculator. You know, it might take you, it might be just annoying enough that it would take a little bit of time. Of course, I can always try and make the numbers big enough that a calculator would just take too long. But my point is just going to be something like this. I might say, don't use a calculator. I might specifically say, I want you to show your work of what you're using from Math 430 to solve this problem. I don't want to just see how good you are at punching buttons into a calculator with this one. This one we should be able to solve by a process because we did learn how to do that. Okay. So whenever I see a system of congruences, the first thing I think of is usually what? Right, the Chinese remainder theorem, exactly. So I usually think of that first. But the requirement in the Chinese remainder theorem is that the moduli have to be pairwise relatively prime. And they are not in this example. So 8 and 18 are not pairwise relatively prime. So therefore, we cannot just use the CRT. We did talk a little bit about systems of congruences where the moduli were not pairwise relatively prime. In this situation, it's actually possible that the system has no solution. Remember that the condition, actually, so do you remember we kind of framed it this way, I believe. We had x congruent to A and x congruent to B, and it was like mod N and mod M. Right, and then the condition was that a solution exists if and only if, and just to remind you, because this goes way back, maybe it's not the freshest thing on everyone's mind right now, but the greatest common divisor of the moduli have to divide A minus B here. So in this case, we just have to check that. The GCD of 8 with 18 is actually, well, you can just, by inspection, it's just 2. Make sure you know how to find the greatest common divisor of any two numbers, even if they're really big. The idea would be, of course, that well, actually, let's talk about that for a minute. If I give you two really big numbers and I ask you to find their greatest common divisor, how are you going to do it? Ben has a good idea in the chat, the Euclidean algorithm, right? We would just use the Euclidean algorithm. So in this case, for example, we would take 18, we would divide it by 8, it would give us a quotient of 2, and then also a remainder of 2. And then we take the previous divisor, which was 8, and we divide it by the previous remainder, we get a quotient of 4, and this time with a remainder of 0. And our GCD is just the last non-zero remainder. So this GCD is equal to 2. And I'll just point out, by the way, that that does divide 5 minus 11. So 5 minus 11 is -6. So we do have divisibility here. Okay, so we just take A minus B, 5 minus 11 there. Incidentally, does anybody know another way of finding the greatest common divisor of two numbers besides the Euclidean algorithm? I just want to remember something from a while ago. Is there another way to do it? Yeah, Tuan has it in the chat. You guys are all over this. Just look at the prime factors. So for example, 8 is, what is it, 2 cubed? And 18 is 2 times 3 squared. And what you do is by comparing the prime factorizations, you just take the minimum number of each prime factor. You just look at each prime factor one by one. Start with 2, then 3, then 5, and so on. Here I see that there is a common factor of 2, but there are no other common prime factors. So that's why I write down 2 now as the answer here. So that's another way to do it. The Euclidean algorithm is great. It's probably the best way, to be honest. But there is also prime factorization that you can use to get the prime factorization, or to get the greatest common divisor. Okay, so now we've got that. So this is an affirmative that this does have a solution because the GCD does divide A minus B. And then we have to remember how to get that solution. That's obviously another important step. So there's a procedure for that. We've actually already started the process right here when we wrote the Euclidean algorithm down. So what you need to do is you need to write the GCD as an integer combination of m and n. So in this case, we would write this as, well, it would be 18 minus 2 times 8. So in other words, it's 1 times 18 plus negative 2 times 8. So we write out the GCD as an integer combination of the two original numbers. I'm just going to remind you that we call these numbers, actually, you know what I want to do? I'm sorry, guys. I actually want to write this a little differently, just so it matches your notes from way back in whenever we did this, February or March. What we really should do is write them in the same order. So I'm going to write 8 times negative 2 plus 18 times 1. Okay, and these two numbers, the negative 2 and the 1, you might remember we had a notation. We called these R and S. There was quite a bit of notation in terms of how to get this expression. So we have R and S, which are the negative 2 and the 1 in this calculation so far. Okay, and then the other number that we need is a number that in the notes, you'll have this back in your notes and you can review it, is the number t. And t is simply a minus b divided by d. So as soon as you know that there is so d is just this greatest common divisor here, sorry. So the greatest common divisor is d. So as soon as you know that d divides a minus b, then there's a quotient, which is going to be an integer. In this case, negative 6 over 3, which is negative 2. So we have that number already, t equals negative 2. Okay, and then we can actually make a
Is it a
solution.
negative 6 over 2?
Oh, 6 over 2, yes, I'm so
Yeah.
sorry. Just checking to make sure everybody's paying attention out there. Right, so this should have been a negative 6 over 2, which is negative 3. Thank you. So t is actually negative 3. And then we just need to recall how to get the solution. So this is actually something, guys, that honestly is probably not a bad idea to have it on a flashcard. The solution is x congruent to a minus nRT, or there were actually two solutions. We can also start with b and do plus MST. So you can go either way with this. Either one of those formulas. So just wanted to throw this up today because it's something to bookmark, to review, make sure you know the expressions that you need here. And this is going to be, by the way, I forgot to mention here, this is a unique solution modulo the LCM of n and m. So it's unique in the modulo of the LCM. Okay, so let's just for the sake of finishing this, let's get an example, or let's just get the calculation going here. So we could choose x in this case to be, let's see, a is 5 minus n, which was 8, times r, which is -2, times t, which is -3. Okay, and so that's 5 minus, what is that? That's actually 5 minus 48, I believe. So that would turn into -43. And then the LCM of, remember the LCM of two numbers is just the product of those numbers divided by the GCD. So I'll just say that again. The LCM of two numbers, you can find it by just multiplying the two numbers together and then dividing by the GCD. In this case, that would be 8 times 18 divided by 2. And so that's going to be 72. And this is a unique answer in mod 72. Let's see what happens if I use the other formula. Just out of curiosity, if I started with the second formula with the 11 in it, right? So I have 11 plus, let's see, m is 18, s is 1, and t is still -3. So we could also get the answer this way. 11 plus 18 times 1 times -3. And sure enough, if you do that calculation, you get -43 again. So either formula will give you the right answer. And it's in mod 72. I might ask you to give me positive answers, right? So let's say I ask you to give me the two smallest positive integers that satisfy our congruence. What would you do to finish this problem? If I ask you for a positive answer, but we've got -43 here, what are you going to do to give me a positive answer? Yeah, we just, Humberto's got it in the chat, so does Tuan. We're just going to add 72 as many times as we want, right? So if we add 72 to -43, we should get 29. That's also a positive answer. Or we could add 72 again and get 101, right? So there's a lot of answers, and there's nothing wrong with taking your answer and checking it, make sure that it actually is correct. So if we took, for example, 29 and we plug it into both of these congruences, we should make sure that it works. You may as well. You've done a lot of work to try to come up with this solution, so why not take an extra 10 seconds and check that it seems to be correct? Yeah. Okay, so anyway, I wanted to review this because, yeah, a few people have mentioned that it's been a while and it's easy to forget things over the course of a lot of weeks. So I wanted to do an example to show you how that would work. Any other questions on this topic? So if the moduli are not pairwise relatively prime, you cannot use the Chinese remainder theorem, right? In that case, we're using this little theory that we derived in class for working with two. Now, if you had several congruences like this, let's say it wasn't just two congruences. If you had 3 or 4 congruences, and in all cases, the mods were not, relatively prime. You had common factors all over the place. What you would do is you would take them 2 at a time. So like you could take these 2 congruences and reduce it down to just this one right here. Right? So we've derived something in mod 72. You could then take that and combine it with a third congruence, right? And so then again, you're only taking them 2 at a time. You're taking this one together with a new one, a third congruence. So unfortunately, you cannot take, if I have like 5 congruences that all have common mod factors in them, the mods all have common factors, you can't just do a one-shot deal to come up with the solution to this list of congruences. You have to take them 2 at a time. So you start with any 2 of them that you like, build up a third one, and then if you had to, build up a fourth one. You just kind of keep adding to what you had already. Does that make sense? So you can't just do it in one step, is what I'm saying. The Chinese remainder theorem is nice because you can just do it in one step. The whole Chinese remainder theorem, pretty much you get your unique solution right at once from a whole list of congruences. I'm not likely to give you like a long series of congruences where you have to do this process over and over, right? Maybe once I might do that, but then I might have, if I wanted to, I could create a problem where you do this first, you get something in mod 72, and then maybe I have another congruence. I don't know. I'm just going to dream something up on the spot here, but let's just suppose I had another congruence, x congruent to 6 mod 7. Right? So now 7 is relatively prime to these other two mods, and it's also relatively prime to 72. So if I really wanted to, I could give you these two, have you solve that, and then combine it with the third one to make a Chinese remainder theorem application within the same problem. Is this making sense? So mod 72 and mod 7, yeah, you can use the CRT for that, no problem. So that I just wanted to review. I don't think I need to well, we'll probably will on Sunday. There'll be something with the CRT in it, but I know most of you are pretty solid on the Chinese remainder theorem. It was part of your cryptography papers. So I know you guys were working on that recently, but we may see that it comes up again in some of this review as well. Let's try another example. Okay, again, we're going to solve this congruence if possible. So for part B, what do I have? X to the 4th plus 5x cubed plus 4x squared minus 4x minus 3 is congruent to 0 mod 52. Okay, let's see if we can sort this one out. Give myself a little room here. So we're going to solve for x if possible. That's the idea here. Well, if there's one thing I hope you guys have learned this semester about congruences, it's that the modulus is really important. Plays a big role in the future of what you're going to be doing to solve the problem, right? It makes a big difference. So I look at that modulus 52. What do you notice about it? What can you say about it? Yeah, it's definitely not a prime, exactly. So we have something that's not prime. So what might we do? If it's not prime, what could we do? Yeah, may as well. Brianna's got a good suggestion. Let's get the factorization going. This is going to be, of course, pretty easy to factor. 52 is 4 times 13. Okay. So a lot of times what we try to do is we try to solve these congruences in each of the smaller mods. In fact, this is, again, alluding back to the Chinese remainder theorem. If we can solve this congruence in mod 4, and if we can solve it in mod 13, then because those are relatively prime, I can use the Chinese remainder theorem to come up with a unique solution in mod 52. So this is a great suggestion. That you guys, a lot of you have already realized. We want to look at the prime factors and consider this equation in those other mods. So let me write it down in these other mods. Which of the two mods do you suppose I should look at first? I mean, I've got 2 of them here to work on. Any suggestions? Yeah, I'd probably start with the smallest mod. Just when you're working in mod 4, right? When you're working in mod 4, it's really, there's only 4 numbers in the universe of mod 4, right? 0, 1, 2, and 3. So there's not very many numbers we even have to think about here. And so I think it's a good suggestion to just, let's look at this in mod 4 first. Anything we can do with this congruence in mod 4 that that maybe we wouldn't have been so comfortable doing with the original mod of 52? Yeah, in mod 4, the 4 is 0 and the 5 is 1. And we can basically take all of these numbers and make them really, really small. Exactly. So let's just do that. So we're going to just break this down, x to the 4th plus x cubed. And then as Brianna says, we can actually even change the -3 to +1. So we're just getting rid of all of the other coefficients. We're just looking in mod 4 at this equation. Okay, so this is a polynomial. It's a degree 4, and we're looking at it in mod 4. Okay, we're asking, well, we're trying to solve for x right now. We don't know if it's possible, or we don't even know there could be several solutions, right? So our job is to figure out every possibility here. What do you suppose I might want to do next? Euler's generalization of Fermat's theorem. So the a to the phi of n is congruent to 1 mod n. That's the Euler's generalization. Let me just write that down in case anybody's not catching what I'm saying here. Right? So as long as a is relative, we do know that this is true. And so the idea here is that we could just use n equals to 4. Humberto, are you able to do your chat to everyone? You're sending me these private notes, but I think it'd be great if everybody could see what you're saying, because you have some really good ideas. I want you to share them with everyone. Yeah, there we go. I'm going to get back to Humberto's suggestion in just a second. So we could certainly take a look at this. Of course, phi of 4 is just 2. By the way, guys, make sure you know how to calculate phi of any number for our final exam, right? We haven't really practiced that today. You should be able to do phi of anything, tau of anything, sigma of anything, right? Just using the multiplicative properties and just knowing how to calculate the basic values of phi, tau, and sigma. It's a really good thing to be able to do. So in particular, using this Euler generalization, if I put in mod 4 right here, this is going to be squared. Okay. However, that's only for the numbers that are relatively prime to 4. And that's only half of the numbers, actually. It's just 1 and 3. So we don't really know anything about x right now. Like, we don't know if it's relatively prime to 4. What if x equals 2? It's possible, right? In theory. So I kind of like Humberto's suggestion as opposed, this is okay. This is certainly insightful, and I'm glad it was brought up because we should know this. But I think it's actually easier here to literally brute force this equation and just try every single possible number. Let's just try it. Let's just try everything. X equals 0. If I put 0 for x, I just get 1 congruent to 0, and that obviously doesn't work. Okay. If I try x equals 1, 1 to the 4th plus 1 cubed plus 1, that's actually 3. It's supposed to be congruent to 0. Nope, that doesn't work either. We're working in mod 4 right now. Okay, so then we can try 2. 2 to the 4th is 16 plus 8 plus 1 is actually 25. Is that congruent to 0 in mod 4? Nope. Right? And we can try 3. 3 to the 4th is 81. 81 plus 3 cubed, 81 plus 27 is 108. We add 1 to that, I believe we get 109. Is that congruent to 0 in mod 4? Nope. So that also doesn't work. And so we have no solutions here for this congruence. So if we have no solutions in mod 4, do we have any solutions in mod 52? In other words, if 4 isn't even dividing our expression, how could 52 divide it, right? It just doesn't going to work. The transitivity of divisibility won't allow that, right? If if 4 doesn't divide something, then 52 certainly doesn't divide something. So there are no solutions here. There are no solutions on this one. No solutions at all, right? So that can happen. You can come up with things that absolutely have no solutions at all. That is certainly a possibility. Any questions on this one? This one isn't really that bad. You just have to break it. The key point here that I'm hoping you're taking away from this is that the smaller the mod, the better. And you can break down a big modulus and look at it using smaller mods because you know that the Chinese remainder theorem is there. We can use that ultimately to solve a system if we get to that point. Here we didn't even get to that point because we didn't have a solution even in mod 4. Okay, great. Let's go, let's do another one. Let's try this one here, part C. I'm going to look at another polynomial. This one I need some parentheses for. So negative 2x squared plus 5x plus 1 quantity squared congruent to 0 in mod 29. That's a 29, sorry. Okay, so let's think about this one. I said on the last example that the modulus is like the most important thing. So looking at this one, we actually do have a prime, right? So the big thing here is that we already have a prime for our modulus, 29. Okay, great. So in a case like this, I'll just remind you about Lagrange's theorem as long as we're talking about it. When you're looking at a polynomial congruence in a prime modulus, the number of solutions is at most the degree of the polynomial. So this is a 4th degree polynomial. If we were to multiply it all the way out, the highest power would be the 4th power. So there are at most 4 solutions here, but there's no guarantee about how many solutions we're going to have. Could be 0, could be 1, could be 2, could be 3, or could be 4. It's not going to be more than that. Whereas if the modulus is composite, then you can have weird things happen where you have like a quadratic equation that has 4 solutions or something like that. So that's just something to keep in mind. But here the modulus is a prime. Okay, any thoughts on, anybody getting any observations here? So there's a suggestion to FOIL it out. And we could do that. We would end up with, quite a bit of terms, I think. And I haven't actually tried it that way. I can't say that it won't work to do that. Maybe if you did FOIL it out, it would just be, when you FOIL out something that's already a quadratic, you're going to end up with, I guess, 9 terms. You'll be able to, of course, combine some of those, but you're going to create yourself a pretty big polynomial. I do want you to think about this. Maybe we can get away without having to FOIL it. What we're really saying here, guys, is that P divides this expression, right? That's really what it said. When we're saying it's congruent to 0 in that modulus, just means that the modulus divides that thing. Can we get anywhere from here based on the fact that the divisor that we're looking at is a prime? Remember, guys, if P divides a product, this is only if P is prime, right? So if P is a prime, And if it divides a product, then it has to divide A or it has to divide B. It's got to divide one or the other. That's more or less the definition of a prime. Or it follows very quickly from the definition. So yeah, the fact that here we're saying that we want P to divide the square, we can actually deduce from that. In fact, this is sort of if and only if P just simply divides the original quadratic without the square. So we don't have to look at the square. So basically what we have, let's just rewrite this again as a congruence, negative 2x squared plus 5x plus 1 congruent to 0 in mod P. Just going to write it in mod P notation again. So now we're down to just looking at this. Okay. So this is the theory of quadratic congruences in a mod prime. So do you remember how we handle this? Remember what we can do here? We form the number D, right? D squared is just that sort of familiar sounding discriminant, right? It's just B squared minus 4AC that you've all seen in your quadratic equations back in high school even. So B squared minus 4AC. In this case, B squared is 25 minus 4 times A, which is negative 2, times C, which is 1. And so that comes out to be 33, I believe. Yeah. And we're working in mod 29 here. So in mod 29, of course, 33 is just the same as 4. Right, so this is actually congruent to 4 because we're working in mod 29. So our D is a perfect square, right? So if we remember, we get this new equation, y squared congruent to D in mod 29. And so since D is 4, then I think everybody can just solve that one pretty much by inspection, that y is either plus or minus 2. Right, so if D is 4, then y is plus or minus 2. And the other important thing that you have to remember here is what y is. Y, this is another equation to just kind of recall, is 2ax plus b. 2ax plus b. So that's the expression for y. And so what you end up with here then, guys, is just two cases. I know it's already 6. I'm going to wrap this up shortly here. So we get a couple of cases out of this. We get, 2 could be equal to 2ax plus b, or congruent, I should say, mod 29. That's one possibility. And then the other case would just be to put negative 2 here. So negative 2 equals 2ax plus b mod 29. And now we just have to try to solve for x. I'm going to plug in what? A is equal to negative 2 and b is equal to 5. So this is just negative 4x plus 5 right here. Same thing on the other side, negative 4x plus 5, okay? And so what I can do is just try to isolate the x. I'm going to subtract the 5. So for this first one, give myself a little more room here. For this first one, if I subtract the 5 across, I have negative 3 is congruent to negative 4x mod 29. And over here, it would just be negative 7 is congruent to negative 4x mod 29. These are linear congruences. Like both of these are just linear congruences, and we know how to solve them. The basic trick that you're shooting for is to get rid of the coefficient here. You want to isolate x, yeah? So in this case, it's actually, you can do it by inspection. But if you couldn't do it by inspection, you can do it by, again, using the Euclidean algorithm. So this is just a quick reminder, guys, at the end of our review session for today, to go back and make sure you know how to solve linear congruences, right? They're not always solvable. Remember, the GCD of A and N has to divide B. So in this case, the GCD of 4 with 29, and well, that's just 1. So of course that divides anything. So these are both solvable, and we can solve them by using the Euclidean algorithm on the A and the N, right? And then running it backwards to basically find an inverse for A. That's how you're going to isolate the X. But in this problem, you probably just noticed that if you multiply through by 7, negative 28 is the same as positive 1, right? So I can multiply through by 7. So that gives me negative 21 is congruent to, again, negative 28 is the same as 1. So that leaves me with X isolated on the right-hand side. Or if we multiply through by 7 over here, we get negative 49 is congruent to X. So we're going to get 2 solutions for X right here. Negative 49 is the same as, if I wanted to give a positive number, I believe it would just be 9. And over here, negative 21, if I wanted to give a positive number, it would just be 8. So I believe that the 2 answers for X, the simplest way to give the answer would be to say that X is congruent to either 8 or 9 in mod 29. Okay. Any questions on that? All right, well, guys, we didn't talk a lot today. I'm going to tell you what we didn't talk about because I'm going to come back on Sunday and make sure that I talk about some of the other things. We did not talk about Diophantine equations, some of those word problems where you solve, you find integer solutions to certain equations. So Diophantine equations, certainly we will try that out on Sunday. We didn't do anything today with primitive roots or how to use indices, right? So, you know, I'm going to give you that table of primitive roots on the front of your exam. And so you might find that useful to then use indices to solve some problem. We didn't really have a lot of time to, you know, talk about, we didn't really use Fermat's little theorem. We didn't do the Chinese remainder theorem today. Those things we've been using regularly throughout the semester, so it might be a little bit more fresh in your mind. Let's see, I'm just looking at some of the other things that I'm going to try to do next time. Oh, the Legendre symbol stuff. I am going to come back to that again and make sure everybody remembers the various properties of the Legendre symbol, and we're going to prove, you know, something kind of like what was on the midterm. I asked you for on the second midterm, we did the Legendre symbol of 6 relative to mod P. I'm going to do one on Sunday night, which is going to be for a different number, I think for 15. The same idea. We'll talk through how to do something like that. So practicing the properties of the Legendre symbol and doing little proofs like that, I'll probably try and do that on Sunday as well. Again, if you can't come on Sunday, I will record that session as well. And so you'll certainly be able to watch this stuff later if you're not able to be here in person. And I might do a little bit more. I did quite a bit today, but I might do a little bit more about, you know, the stuff that we did at the end, the perfect numbers, the representations as sums of squares, that kind of thing. Yeah, guys, problems similar to the midterms. Keep in mind, you have a midterm and a sample midterm, and then another midterm, and then another sample midterm, right? And then a sample final. I mean, it's no shortage of problems to look at. It's probably too many. It'd be better if we had less problems, but I'd rather not be that professor who doesn't give you enough stuff. I want to make sure you have plenty to look at. Don't feel bad though. I don't want you to show up Wednesday thinking, gosh, I didn't look at everything that was out there, because that shouldn't be something that destroys your confidence, right? You're not probably going to have time. I know you've got other classes, you've got other finals. You're not going to have time to do everything. Focus on those things where you feel that you need practice. And certainly things that on the midterms, maybe you didn't quite get straight the first time. I think those would be good to go back and look at again. And then the sample final, just make sure that you feel confident with those things. And, you know, some of the other stuff, if you've got time to do the practice quizzes, or if you've got time to look at the group works, that'd be great, you know, but get some sleep too, you know, get some rest, take care of yourself, make sure that you're pacing yourself and treating yourself well, because you want to feel good when you come in on Wednesday as well. So I think in terms of feeling good, I should probably take a break because I have 3 hours of office hours starting at 7. So I think maybe resting my voice for 45 minutes right now would be good for me to do. And then if you do have any follow-up from today's review that you want to go over with me tonight, that'd be great. There's also homework. If you've got some questions on the homework, I'm obviously going to be very happy to help you with any of that. And so feel free to jump into Zoom over at my office hour address in just a little while. Okay. Okay, I am going to call it a day at this point and say thank you for being here today. And I will look forward to seeing you all again, well, whenever I see you. I'll see you when I see you. All right, have a great rest of your afternoon. Thanks for coming. I hope this was useful. I'll stop recording now and I'll get